The noble gases are the most stable group of elements. They are all colorless and odorless. With a few exceptions, they are inert, meaning they do not readily react with other elements. Helium is the second most abundant element in the universe, but it is rare on Earth. Because it is so light, it easily escapes the atmosphere. Most earthbound helium is in natural gas deposits deep underground. Neon is best known for the colorful lights of Broadway and Las Vegas. Not known to form any compounds, neon is completely inert. Argon is the third most abundant gas in the Earth's atmosphere. It is often employed to create inert environments for industrial processes and light bulbs. Krypton is occasionally combined with argon to create unreactive atmospheres for industrial processes. It is also used for lighting in high-speed photography. In 1962, scientists were able to form a compound between xenon and fluorine, making xenon the first noble gas to react with another element, and proving that even the noble gases can form compounds under the right conditions. It is most commonly used in high-powered and strobe lights. Radon is the only radioactive noble gas. It was first observed as a decay product of radium. It may present a health hazard if it is found inside a house. To understand why it is so difficult for the noble gases to form compounds, let's take a closer look at the periodic table. The elements are listed in the order of their atomic number, which represents the number of protons in an element's nucleus. In its ground or normal state, the nucleus is surrounded by a number of electrons equal to the number of protons. As the atomic number increases, generally so does the size and mass of the atoms. Reading from top to bottom, each horizontal line on the table is called a period. Each period represents the number of electron shells normally occupied by an element's atoms. For example, a krypton atom has 4 electron shells, so krypton lies in period 4. Meanwhile, a radon atom, in period 6, has 6 electron shells. Reading across the table from left to right, the vertical lines of elements are called groups. Elements in a group have the same number of electrons in their outermost electron shells. These are called valence electrons, and they dictate how elements interact. Elements in the same group generally interact with other elements in similar ways. None of the elements greater than atomic number 83 are completely stable. All of them, including radon, are radioactive. All the noble gases reside in group 18 because each one has a full valence shell. A helium full shell has 2 electrons. All the other noble gases have 8 electrons in their outermost shell. Because the noble gases need no electrons to be stable, they rarely react with other elements. Only the heavier noble gases form compounds, and then only in special laboratory conditions. Krypton, xenon, and radon will react because as you move down the group, an atom's hold on its valence electrons becomes weaker. The stability of the noble gases is actually a useful property. These gases are used in many situations where an unreactive gas is needed to maintain a safe and constant environment. Industrial processes such as welding rely on atmospheres of noble gases to prevent explosions. And vintners use argon to prevent wine from turning to vinegar. All of the noble gases will conduct electricity. Neon may be the most familiar gas used for lighting, but argon, krypton, and xenon also fluoresce, and combined, they create many different colors.
Element number 2 on the periodic table is helium. The atomic symbol for helium is He. Helium is a very light, inactive gas that is odorless, colorless, tasteless, and non-flammable. Helium gets its name from the Greek word helios, which means sun, because helium was observed on the sun before it was found on Earth. Helium is classified as a noble gas. It lies in the periodic table's first row, period 1. Each atom of helium consists of 2 electrons that surround a compact nucleus, which contains almost all the atom's mass. In the most common form of helium, its nucleus has 2 positively charged protons, plus 2 uncharged neutrons. 2 negatively charged electrons balance helium's 2 protons. These electrons are found in a single orbital shell surrounding the nucleus, the sphere-shaped 1s shell. An s shell can only hold 2 electrons, so helium's electrons fill the shell. This completely filled electron shell makes helium, and the other noble gases, extremely unreactive with other elements. In this experiment, a red balloon is filled with pure helium gas. Helium is very light, about 7 times less dense than ordinary air. Released at the same time as a blue balloon filled with argon, the helium balloon rises quickly into the sky because it is so much lighter than the surrounding air. Meanwhile, because argon is about 35% denser than air, the blue balloon falls to the ground. Helium is most widely used in party balloons, scientific balloons, and blimps. Combined with oxygen, it is used by deep-sea divers in scuba tanks. Helium may also one day find wide use in superconducting electrical systems and nuclear power plants. Space is often considered the final frontier for exploration. Since 1961, NASA has made many efforts to extend the United States exploration into space. A reusable vehicle designed for regular missions, the Space Shuttle traveled into space multiple times. The shuttle could not have been realized without the element helium. To escape Earth's gravity and enter orbit, several engines and rockets worked together to accelerate the shuttle to a speed of almost 7 miles per second. The shuttle has a main engine at the back of the fuselage, which is fueled by a large external tank containing liquid oxygen and hydrogen. 2 solid rocket boosters, or SRBs, are on the sides of the external tank. Its main engine and the rockets power the liftoff. After about 2 minutes, the rocket boosters separate from the shuttle and fuel tank and fall into the ocean. Once recovered, NASA will use them again. About 9 minutes after launch, the external tank disengages from the shuttle. Unlike the rockets, the tank burns up as it descends through the atmosphere. About a minute later, the Orbital Maneuvering System, or OMS, fires to place the shuttle into orbit. This system requires helium to operate. Without it, gravity would pull the shuttle to Earth. The OMS requires some creative engineering to operate in the vacuum of space. First, NASA had to come up with a way to create combustion in the absence of oxygen. The solution is to mix fuel with an oxidizer, a compound that has the same effect as elemental oxygen but is easier to contain. The liquid fuel and oxidizer are kept in separate tanks. When they combine, they produce a volatile gas that powers the shuttle. Another feat of engineering is the pump. A pump needs to move the fuel and oxidizer out of their tanks and into the engine. But a mechanical pump is likely to break down or require adjustments in space. So NASA engineers developed a helium pressure pump for the OMS. Helium kept at high pressure in a single tank is attached to the fuel and oxidizer tanks. To ignite the OMS, helium gas is released through a series of valves and tubes. It forces the other liquids from their tanks into the engine, where they combine and ignite. Helium is ideally suited to its role in the shuttle. Because it has a full valence shell, it is completely inert, so there is no danger of it reacting with the fuel or the oxidizer. This prevents any loss of usable fuel, as well as minor damaging explosions. Any non-reactive gas might serve the same purpose, but helium is the best choice because it is so light. Every extra pound of weight the shuttle carries requires more energy to get into orbit. As one of the lightest substances known, helium powers the OMS with the least amount of weight. At the end of a successful mission, the shuttle astronauts fire the OMS one last time to return to Earth.
Roger, you're on center line on glide slope, sir.
Once inside Earth's gravitational field, the shuttle essentially falls to the ground. Thanks to helium, the astronauts could enter space and return home safely.
Element number 10 on the periodic table is neon. The atomic symbol for neon is Ne. An odorless and colorless gas, neon gives off an intense red light under high voltage. Neon is named from the Greek neos, meaning new. Neon is classified as a noble gas. It lies in the periodic table's second row, period 2. Each atom of neon consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of neon, its nucleus has 10 positively charged protons, plus 10 uncharged neutrons. Neon has 10 negatively charged electrons to balance its 10 protons. These electrons are found in 2 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, helium. Helium has 2 electrons distributed in 1 orbital shell. Neon has 8 more electrons than helium. The first 2 electrons are found in the sphere-shaped 2s orbital shell. The final 6 electrons fill the 3 lobe-shaped 2p orbitals. As the 2s and 2p orbitals are all filled, neon's second-level valence shell is complete. This makes neon and the other noble gases very stable and extremely unreactive with other elements. Neon gas is contained within this discharge tube. The pressure of the contained neon is low enough and the voltage across these 2 electrodes is high enough for the neon to conduct electricity. Notice how it emits a characteristic orange-red glow due to excitation of the electrons when placed in the path of the electricity. Neon is the 4th most abundant element in the universe, but only a very small fraction of neon is found in the Earth's atmosphere. Neon is best known as the source of the reddish-orange glow in neon lights, but has also been used to make voltage detectors and TV tubes. Ever since Thomas Edison invented the incandescent light bulb, our world has been an electrical one. Scientists were fascinated by how naturally occurring elements produced light. They began to experiment with other gases. In 1910, French scientist Georges Claude sent an electrical current through neon gas, to produce the first neon lamp, and the neon sign was born. White light was practical, but colored lights were daring and glamorous. They did more than light the way. They mesmerized with their glow. The first neon sign in America was displayed in Los Angeles, California. People were so fascinated by it, they literally stopped traffic to see it. Today, we see neon all around us in those brightly glowing signs that make everyday words like pizza and burgers shine. Nowhere do they shine more brightly than in Las Vegas. Neon transforms this ordinary desert into one of the brightest spots on the planet.
Well, people are like insects. They just love light, and they're drawn to it, and they want to see what it's all about. And so the casino operators and everybody here put a lot of light out, and it just draws people in. It just says, we're having a party here, come on in.
It takes a unique blend of science and art to bring Las Vegas to life, and the properties of neon make it possible. Neon is an inert gas, which in its natural ground state is odorless and colorless. However, when an electric current runs through a tube filled with the gas, that all changes. The energy supplied by the electrical current is absorbed by some of the electrons in neon's outer shell, and they temporarily jump to a higher energy level. After a brief period of time, the excited electrons fall back to their original location. The energy they lose as they return to their shell is emitted as light, causing neon to glow. The wavelength of the light energy determines the color of the fluorescence. While all those brightly colored signs are commonly known as neon lights, it takes other gases individually and combined to achieve over 150 different colors. Neon produces a familiar reddish glow, while Krypton glows a silvery white, and Xenon green-blue. Artists known as benders produce neon signs by bending lead glass tubes into various shapes. The tubes can be bent into shapes or into letters to form words. Once created, neon signs can last for decades. The beauty of light has lured man ever since he harnessed the power of electricity, but nothing catches the eye quite like neon. Element number 18 on the periodic table is argon. The atomic symbol for argon is Ar. Argon gas is shown rotating within a discharge tube. It is maintained at a low pressure to conduct electricity, and it emits a characteristic bluish light. Argon is a monatomic noble gas, which is colorless and odorless in its natural state. The name argon comes from the Greek argos, meaning idle or inactive. Argon is classified as a noble gas. It lies in the periodic table's third row, period 3. Each atom of argon consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of argon, its nucleus has 18 positively charged protons, plus 22 uncharged neutrons. Argon has 18 negatively charged electrons to balance its 18 protons. These electrons are found in 3 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, neon. Neon has 10 electrons distributed among 2 orbital shells. Argon has 8 more electrons than neon. The first 2 electrons are found in the sphere-shaped 3s orbital shell. The final 6 electrons are distributed among 3 lobe-shaped 3p orbitals. A p shell can only hold 6 electrons, so argon's electrons fill the shell. This completely filled electron shell makes argon and the other noble gases extremely unreactive with other elements. In an argon arc furnace, an electrical current of approximately 100 amps is used to strike an arc between a movable tungsten probe and the objects to be melted. This arc is conducted by a low-pressure atmosphere of pure argon, which glows like a pale green flame. Using this technique, temperature in excess of 3,000 degrees Celsius can be achieved. Because argon is completely unreactive, the incandescent target is protected from oxidation. Argon is most useful for creating an inert or unreactive atmosphere in various situations. It is used to fill incandescent and fluorescent light bulbs to prevent oxygen from corroding the hot filaments. Argon is also used for arc welding and similar processes that require shielding from atmospheric gases, or when explosion or other forms of oxidation may pose a problem.
Element number 36 on the periodic table is krypton. The atomic symbol for krypton is Kr. Here, krypton gas is rotating in a discharge tube. It is colorless and odorless in its natural state, but it emits a silvery white light as it conducts electricity. The name krypton comes from the Greek kryptos, meaning hidden. Krypton lies in the periodic table's fourth row, period 4. It is classified as a noble gas. Each atom of krypton consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most common form of krypton, its nucleus has 36 positively charged protons, plus 48 uncharged neutrons. Krypton has 36 negatively charged electrons to balance its 36 protons. These electrons are found in 4 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, argon. Argon has 18 electrons distributed among 3 orbital shells. Krypton has 18 more electrons than argon. The first 2 electrons are found in the sphere-shaped 4s orbital shell. The next 10 electrons fill 5 clover-shaped 3d orbitals, and the final 6 electrons are distributed among 3 lobe-shaped 4p orbitals. A p shell can only hold 6 electrons, so krypton's electrons fill the shell. This completely filled electron shell makes krypton and the other noble gases extremely unreactive with other elements. Here, low-pressure krypton is contained inside a discharge tube. 3,000 volts are applied to the 2 electrodes. Excited, the electrons in the gas emit a characteristic silvery white light as they fall to their ground state. Krypton is used for lighting for high-speed photography. Some fluorescent light bulbs are filled with a mixture of krypton and argon gases. Krypton also goes into luminous signs that glow with a greenish-yellow light. In 1960, the length of the meter was defined in terms of the orange-red spectral line of an isotope of krypton. Recently, a helium neon laser replaced krypton as the standard. A wine glass crashing to the floor breaks into a million pieces. The rhythm of rainfall can be heard and seen. By removing the barriers of time, high-speed photography provides a glimpse into a hidden world. It's a world where common occurrences become extraordinary. The idea is simplicity itself. When recording, speeding up film causes images to slow way down. That's the basic principle of fast-motion photography. But things often aren't as simple as they look. Step into a high-speed studio and enter a world of Hollywood high technology. A normal camcorder records images at a speed of 30 frames a second. In slow-motion photography, the idea is to expose the film at much higher speeds.
Regularly, we shoot it at over 10,000 frames a second. This is what 1 second's worth of film at 10,000 frames a second looks like, as opposed to real-time, 1 frame a second. So it's very impressive, and we can shoot anything up to 250,000 frames a second, which would stop a bullet.
In the past, only Superman could stop a speeding bullet. Now, any average Joe with the right camera can be Superman.
The basic mechanism of any high-speed camera is a very, very powerful motor that rips the film through the camera at enormous speeds, anything up to 300 or 400 miles an hour. So you need an enormous amount of light in order to keep the exposure on the subject.
The enormous light requirements of high-speed photography require anything but an average light source. Special lights using Krypton are put to work. A Krypton light source produces an exceptionally bright light. Together, several provide enough light for high-speed filming. Krypton's brightness and its extremely fast response to an electric current make it invaluable for quality high-speed photography. Film shot at high speed is played back at normal speed. This technique expands time and makes things appear to move much slower than in real life. The result is a breathtaking marriage of technology and art.
We were recently working with somebody shooting a Taekwondo black belt as he karate chopped through slates and wood. And what we discovered was that there was an enormous shockwave that traveled up his arm as he came into contact.
High-speed photography can make a scampering dog appear to run gracefully. It shows us that cats really do land on their feet when dropped from a low height.
High-speed photography for people in commercials is a technique that enables everyday activities to gain a grace and a beauty that you wouldn't imagine.
Element number 54 on the periodic table is xenon. The atomic symbol for xenon is Xe. Xenon is a colorless, odorless gas that conducts electricity at low pressure. The name xenon is derived from the Greek xenos, the word for strange. Xenon is classified as a noble gas. It lies in the periodic table's 5th row, period 5. Each atom of xenon consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most common form of xenon, its nucleus has 54 positively charged protons, plus 78 uncharged neutrons. Xenon has 54 negatively charged electrons to balance its 54 protons. These electrons are found in 5 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, Krypton. Krypton has 36 electrons distributed among 4 orbital shells. Xenon has 18 more electrons than Krypton. The first 2 electrons are found in the sphere-shaped 5s orbital shell. The next 10 electrons fill 5 clover-shaped 4d orbitals, and the final 6 electrons fill 3 lobe-shaped 5p orbitals. As the 5s and 5p orbitals are filled, Xenon's 5th-level valence shell is complete. This makes xenon and the other noble gases very stable and extremely unreactive with other elements. Xenon conducts electricity at low pressure. Pressurized xenon is contained within a discharge tube. Discharge tubes are usually made from glass and hold 2 electrodes sealed at each end. A voltage is applied to the 2 electrodes. The pressure and voltage of the contained xenon is high enough for the xenon to conduct electricity between the electrodes and burn with a characteristic blue-violet glow. Due to the bright white light produced when excited, xenon is most commonly used in strobe lights and other powerful lamps. The light emitted from xenon can also be used to kill bacteria and power certain types of lasers.
Element number 86 on the periodic table is radon. The atomic symbol for radon is Rn. Radon is a colorless, odorless gas present in the Earth's crust. It has a short half-life, but is constantly produced by the radioactive decay of uranium. The name radon comes from radium, because it was first observed during radium's radioactive decay. Radon is classified as a noble gas. It lies in the periodic table's 6th row, period 6. Each atom of radon consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most common form of radon, its nucleus has 86 positively charged protons, plus 136 uncharged neutrons. Radon has 86 negatively charged electrons to balance its 86 protons. These electrons are found in 6 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, xenon. Xenon has 54 electrons distributed in 5 orbital shells. Radon has 32 more electrons than xenon. The first 2 electrons are found in the spherical 6s orbital. The following 14 electrons fill the 7 lobe-shaped 4f orbitals. The next 10 electrons fill the 5 clover-shaped 5d orbitals. And the final 6 electrons fill the 3 lobe-shaped 6p orbitals. Radon is extremely unreactive with other elements because its valence shell is complete. Radon enters buildings in many ways. Trapped indoors, it becomes concentrated, particularly in basements that have little ventilation. Radon's radioactivity makes it dangerous to living things, but it is possible to test the level of danger. This radon detector is a long-term alpha-track device. It can be placed in areas that may be exposed to radon. After several months, the detector is analyzed for evidence of radon. The sensitive detector surface in this device is damaged by the alpha particles given off as radon decays into other elements. The amount of damage determines the level of radon concentration. Even though radon may present a health hazard in a home, hospitals sometimes use small amounts to treat forms of cancer. At a small spa in France, naturally occurring radon is used as an alternative therapy for everyday ailments such as allergies and indigestion.